In the full course, we showed you how to model systems 1, 2, 3, and 4, and in the previous video, we showed you how to model system 5 using the compliance wizard. The compliance wizard works, though it uses a different type of system and might cause confusion. So in this video, we are going to show you how to model system 5 in the conventional way that most reviewers expect to see when they see packaged VAV. Here we're going to model ASHRAE 90.1 baseline system 5 packaged VAV with reheat. The first step we're going to take is we're going to import system imports for VAV 5 through 8, which includes supply air reset, optimum start, VAV fan we made in other videos. Yes. And it skipped them because I had already imported them into this file. The steps are the same. We're going to follow the template we've modeled in the other videos and start by a file that we created in the wizard. We're going to edit the first system and the first system only. From the wizard, we have the correct system type, packaged variable volume. We set the system sizing ratio to 1 here because we're going to edit the coil sizes. The next thing we're going to do is we're going to go to the cooling tab and ensure the cool sizing ratio is 1.15. We have to have a 20-degree delta T from our set point in the rooms, which was 75. It just so happens that this is 55 degrees, which is brought in from the wizard. One of the things that we have to do is we have to model a specific type of cooling reset per ASHRAE 90.1. But what we've done is we've created the supply air temperature reset. We have the supply air reset temperature that we made in the other video, and we imported that in the beginning of this lesson. The next thing is the heating tab. We have to change the heat source to the hot water loop and set the heat sizing ratio to 1.25. Again, this is per ASHRAE 90.1 baseline requirements. So we did the cooling tab, the heating tab. Next thing is the outdoor air tab. Depending on your system type and the climate zone, you may have an outside air economizer. We've been modeling Chicago, and that requires an outdoor air economizer with a dry bulb limit of 70. It has no compressor lockout, and there should be no enthalpy high limit. It should not say 0, it should just be blank. If it says something, restore the default. Right here we have it at the default. Next thing is the fans tab. There's several things that we have to change here, and we have to change them in the right order. It's a variable speed fan that follows a defined fan curve. From another video, we created this fan curve and put that into a file. And now we have the curve for the 90.1 VAV fan. The fan follows a specific unloading curve that will edit its energy consumed based on its volume. We also have to ensure that the fan cycling is set to cycle on any for the night cycle control, if you didn't do this in the wizard or in an earlier setup. Back to the main fan power tab. Systems of 10,000 CFM or more require optimum start. We covered this in an earlier video and created the import file. And we select this fan schedule that we just imported. We may or may not have optimum start required, and so that will be for us to determine later. However, if we start with optimum start, that won't necessarily hurt anything. Optimum start is allowed, it's just required when it's over 10,000 CFM on the system. So far, this is what we can model for the system before we require any calculations. We are going to require one system per floor for system 5. That was brought in from the wizard. We also are required to set up the minimum VAV flow per zone. Depending on the standard, many of the standards require a ratio of 0.3, which is brought in from the wizard. The ratio of 0.3 means the VAV box can close down to 30% of the flow of the room. The minimum design flow is unrelated to that and is probably going to end up closer to 1 CFM per square foot for most rooms. So that is unrelated. And then of course we'd want to look at our other zones and ensure that they follow the same thing. Most of the time, all of the zones will be the same. We have the minimum flow for the VAV box defined. The next thing we have to do is define the efficiency and the fan power. We can't define those without knowing how big our system is. This is a step that you would take when you're closer to the end of your model, where you have the lights updated, insulation, and the glazing defined per 90.1. We will assume that the envelope and the internal loads are defined. We go to simulate. We'll view the detailed simulation output file. And we want to jump straight to the SVA report like we've done in our other videos. Right here we can see that the cooling capacity is 406 kBTUs. The supply CFM is 10,300. That would mean that we need optimum start for the system. The two important numbers are going to be the cooling capacity and the supply CFM here. We need to take the cooling capacity and look at table 6.8 in your version of ASHRAE 90.1. We're using the 2010 version for simplicity, as it's still relatively common and it's very similar to other standards. Navigating to ASHRAE 6.8.1a, we look at air conditioners, air-cooled, and it was 400,000 BTUs per hour, approximately. And the heating type is all other, and that brings us to a 9.8 EER. One tip here is if you weren't sure, you could always take the worst value and that would be acceptable. You see 9.8 EER here for this particular system size. Going back to eQuest, We want to enter the EER, and we find that under unitary power, eQuest requires this electric input ratio. There's several ways to calculate this. The input ratio is just the inverse of the COP. So the most basic way of calculating EER to the cooling electric input ratio is to take 3.413 divided by the EER. If we take the calculator, 3.413 divided by 9.8, the result is 0.3483, rounding to the fourth digit. Just somewhat close to the number brought in by the wizard. And click on another cell just so that the entry completes. As we mentioned, the fan CFM also dictates a number. There are multiple ways to calculate the fan power. I calculate the ASHRAE 90.1 fan power using a tool that I wrote. I wrote it specifically for eQuest. So you go to Energy-Models.com. This is a free tool. You don't need to log in. ASHRAE 90.1 fan power, 10,300. The fan filter credits are another topic that you can add that are outside the scope of this course. Basically, if you have extra filters in your proposed model, you're allowed to take extra fan power to offset the power that the proposed requires. Select variable volume and calculate. It gives us the total brake horsepower. In terms of eQuest, it gives us a kW per CFM, 0.00106. And then we go to enter the kW per CFM in eQuest, and you find that you can't do it. What we have to do is restore default on this static. And then we have 4 digits here. Rounding up, it's 0.001068. You'll notice the delta T changes along with that. We have the fan EER fan curve set up from before. And now we have the fan power set up as well. The last step is defining the heating efficiency, and the heating is provided through hot water heating and therefore through a boiler. Click done. We go to the water side HVAC here, and we have the hot water loop and a boiler that was brought in. That completes the airside system for ASHRAE 90.1 System 5 Packaged VAV. In the full course, we show you how to model the boiler portion of this system. Additionally, you get a copy of the downloads that we showed in the beginning of the video, and there is a import file that you can use to bring in an example of the VAV system that we just modeled. So if you like that course, we have all of the systems outlined using the compliance wizard and how to create them manually. Please support this ongoing effort to create a massive eQuest library by signing up and sharing with your friends. Thank you.